Same here. I can't hear you. Nothing.
Testing, testing.
Yes, we can hear you.
Okay, you're finally hearing me, but that's weird because I'm using my cell phone as a speaker. So I don't know what happened, but that's not good. But at least it's working for right now. So we found a workaround. Hopefully y'all can hear me well enough for the rest of the period. Anybody have any questions before we get started? Sorry about that. Whoa.
Yes, I have a question.
Go for it, John.
I think I misunderstood your due date for the chapter 6, 7, 8 test. And I
Gotcha.
tried to do it on Friday and I was already locked out.
Yeah, I thought I was supposed to have allowed that date. Let's double check. I'm gonna pull that test up right now and change it. Looks like test 7. Is that what you're talking about?
6, 7, and 8.
Okay, that one, gotcha. Yeah, I did set that one to the 15th. I'll go ahead just because I'm doing this for the practice test as well, by the way. I'm gonna go ahead and set it for, let's make it, whoa, that was really bad. So today is actually the 20th. I'm gonna set it for a Wednesday at 11:59 p.m.
That's fine. I'm gonna get it done tomorrow. I was ready to go and I just couldn't do it.
Yeah, no problem. And chances are there's a lot of people, because I went in the grade book today and saw a lot of missing grades. I just did the practice test. Now I'm going to change the actual test as well.
I also have another question. When is the last day that we can get all the homework done?
I think I've got it set up where it has to be by the 5th or something like that. The 4th is Monday.
Yeah.
And usually I do it like by the second day of the week, just because it's kind of problematic. But if someone's really in dire need of a grade, sometimes I can let them do it a little later. You just have to let me know if you're going to do it later than that.
I've requested 2 days off of work trying to catch up. But
Gotcha.
So in addition to taking the test on Friday, I tried to do the homework section on Friday, and apparently the Pearson service was out on the homework.
Yeah, they've had some outages this time that have not been cool. I tell you what, I'd worry more about getting your test grades decent if come the end of the semester. I know I'm putting this on recording, so it's not very useful, or it's kind of hidden. But anyways, when the end of the semester's up, when I look at your face-to-face grades on your test and your test grades in general, if I see your homework's pulling you down, I'll often throw out the homework to see if if you've completed most of them, it's not a big deal. But if you missed a couple, it's not bad. Or if you've just got some bad grades, but you completed all of them, I don't allow the homework that much power. In fact, I often allow it less power than the syllabus says. As long as people have attempted to do all of them. If somebody did none of them, then they better be perfect on their face-to-face test. But just keep that in mind. It's more important that you do well on the test, the online as well as the face-to-face tests.
Okay.
So don't get too bogged down in trying to play catch up.
I'm not.
Okay.
All right, thanks.
You're welcome. Anybody else before we get started? All right, well, I'm going to go ahead and get us started.
I had a question, Professor. He was just asking about the test that was due on November 15th, correct?
Yeah, it had the 15th on there, so I might have did something wrong, but I made it now to the 22nd. So if anybody missed it, it's test 6 on chapters 7 and 8. That's now available till Wednesday of this week at 11:59 p.m.
Okay, thank you.
You're welcome. All right, so I am connecting you with my phone. No, with my iPad. I have some friends that say phone instead of phone. It cracks me up. So let's see if I can share. It looks like it's saying, oh, that was the fastest share ever. Hopefully y'all are seeing that. Okay, so when we last met, we had gotten into the idea of the simple harmonic oscillator. I will remind you what that is. So what we found is in the certain case where you had Newton's second law, which is the summation of the forces in a certain direction, let's say x, is equal to m d2x over dt squared. That's what you have to use really if you're talking about accelerations that aren't constant. You have to use at least dv dt, but maybe d2x over dt squared. When this is the case, then you could get m d2x over dt squared is equal to negative kx. That's Hooke's law. And then if you pull it over here to the same side and divide both sides by m, you get d2x over dt squared plus k over m x is equal to 0. That is the simple harmonic oscillator. So it's really worthwhile for you guys to take the time and commit that differential equation to memory. Notice it's just a constant times the second derivative. In this case, I actually already divided through by m, but if you had a constant times the first second derivative plus a constant times the x itself, and then that's equal to 0, then that's the simple harmonic oscillator. And what we find out is the equation that solves it is x of t is equal to a cosine omega t plus phi. So that is the actual solution. And then, of course, with all differential equations, remember, they're sort of like a second order differential equation. Since it's been a derivative has been taken twice, you sort of have to integrate twice to solve it. And each time you integrate, you normally introduce a integration constant. So since this is a second order differential equation, you'd expect that you need two initial conditions to evaluate the two constants. And that's right. So I'll say n need two initial conditions, actually. And I use the phrase initial conditions because everybody uses the phrase initial conditions. And that implies that these are conditions at t equals 0. But to be honest with you, the t equals 0 conditions are ideal, but they're not necessary. You could have x at 2 seconds and x at 2.5 seconds, and that should be enough to actually get it for you. So as long as you have that, then you can do it. You also need to realize, though, that this gives us omega is equal to the square root of k over m. So all of the stuff that I underline here, you need to keep in your brain and memorized. Okay. So a constant times the second derivative plus a constant times the 0th derivative is equal to 0, gives you this solution with this omega defined, and it's called the simple harmonic oscillator. Now, what I'm going to do, and I didn't do this last time, is I'm going to actually use initial conditions to solve for this arbitrarily. So let's say our initial conditions, and I'll call this an example. If x of t equals 0, which we define to be x of 0, is equal to x sub 0, and v of 0 is equal to v0, then what are a and phi? So there's our question. Here's our solution. So what we're going to do is we're going to say x of t is equal to a cosine omega t plus phi, and we know omega is equal to the square root of k over m. Now, what we're told is that x0 is equal to a cosine of 0 plus phi, which equals a cosine phi. And what we're also told is v0 is equal to, now what I'm going to do is take the first derivative of x of t, because the derivative of x with respect to time is the velocity. So the derivative of x of t is negative a sine, excuse me, is negative omega a times the sine of omega t plus phi, but that's 0 plus phi because we're evaluating at t equals 0. So that's what happens here. And in this case, we get negative omega a sine phi. Okay. So what I can do now is I can take a times the sine of phi and divide it by a times the cosine of phi, and that's just going to give me the tangent of phi. But notice a cosine of phi is actually equal to x0, so that's going to be down here in the bottom. And then a sine phi is going to equal negative v0 over omega. So that's negative v0 over omega. So we get tangent phi is equal to negative V0 over omega x0, or phi is equal to the tangent inverse of negative V0 over omega x0. So that's one of our answers. Now, the other thing is we can go back and use the fact that x0 is equal to a cosine phi, and we can use this that we solved for phi, we can use that to create a triangle, and the triangle would look like this. Notice a negative phi. So this is phi, and we can treat it sort of like this side is negative V0 and this side is omega x0. Then this side will be the square root of V0 squared plus omega squared x0 squared, like that. So in this case, we can now say that x0 is equal to a, and then times the cosine of phi, where cosine of phi would be omega x0 over the square root of V0 squared plus omega squared x0 squared, like that. And that gives us that a is actually equal to omega. Yeah, because when I pull the a over to the other side, I'm actually going to get x times the square root thing, but that's going to cancel out. So I get the square root of V0 squared plus omega squared x0 squared. All of that's going to be divided by omega. And then technically it would have been divided by x0, but I already had an x0 up top. So it should just be that, which you can also write as the square root of V0 over omega squared plus x0 squared. Because when I pull it up on the top, I can pull it inside the square root by squaring the omega, and I get V0 over omega squared plus, then the omega squared cancels out and get that. So there's my two answers. I'll go ahead and write the other one right here. A is equal to the square root of V0 over omega squared plus x0 squared. Any questions on that? So this actually works if they tell you specifically a position when t equals 0, and they tell you specifically a velocity when t equals 0, then you can just blindly apply these. I've never once committed them to memory personally. So what I actually do is I derive them like this as soon as I come up with that type of formula. So you don't actually have to memorize these extra parts, but you can if you want. And actually, if you solve enough problems, sometimes the formula gets stuck in your head, or if you derive it enough times, sometimes the formula gets stuck in your head. But this is basically a general solution to it. So hopefully that helps. Anybody have any questions on that, or how any of that was done or anything? Okay, let me put up, I'm going to put up your chat just in case someone's saying something to me and I don't know it. Okay, I got your chats up now, and it doesn't look like anyone said anything since y'all announced that you could hear me, so we should be on the roll. All right. I'm going to go ahead and break this off right here, and that's the end of that example. So we should be able to use that. Now, there was a problem early on where we were told that a car had a mass of 1,200 kilograms, and I said there was, I think actually with the problem, I think I said there was 300 kilograms of people in it. So actually, let me check that. I'm gonna pull up the original assignment set where we worked this problem. I think that was on 11/15. And You guys should be seeing this now. Hopefully you are. Yes, you are. Okay, so this are notes from last time. And do I see the car? Do I see the car? Yeah, a car sinks by 4 centimeters when 300 kilograms of people sit in the car. What is K? And how much would the car sink if 500 kilograms was put instead of 300 kilograms? So we're going with that same example in some sense. So what I'm going to do is I'm going to steal this. I'm going to say like this. I'm going to say copy, and now I'm going to pull this back up and see if it lets me paste. And it did. And in this case, this isn't actually the problem we have, but I wanted that introductory information. So what I'll do is erase all this stuff right here so we can figure out what K is if we need be and all that good stuff. Okay, and I lost a gram, part of my G on that kilogram there, so I'll fix that. So we're starting with this problem, and what I'm going to say is, assuming the car hits a bump, what is the period and frequency of the rocking that this car experiences? So assuming the car hits a bump and its springs, well, I'll say its shocks are bad. Evidently, I'm going to write bad. There I go again. Bad. What will be the period and frequency? Okay. Now I'll remind everyone that we discovered our K was 7.35 times 10 to the 4th Newton per meter. Yes. So K was 7.35. And actually, I think it was times 10 to the something. This 7.35 times 10 to the 4th. Yes, almost forgot it. Times 10 to the 4th newtons per meter. Let's do our solution. So what we've learned from the differential equation is that omega is equal to the square root of K over M, and that omega is also equal to 2 pi F. So F is equal to 1 over 2 pi times the square root of K over M, which equals 1 over 2 pi times the square root of 7.35 times 10 to the 4th newtons per meter divided by, now in this case, I'm going to try to remind myself what, if anything, I used for the car. I think I used 1200, but actually it wouldn't matter if I didn't actually solve that part, which it looks like I didn't. So that's cool. Yeah, that looks like it's okay. So I'm going to say the mass of the car is in fact equals 1200 kilograms. Okay, so I'll put the 1200 down here. And now we have newtons per meter divided by kilograms. And a newton is a kilogram meter per second squared. So we're actually just going to get per second squared under the square root, which gives us hertz, basically. So let's do this. I'm going to do square root. And I'm going to do 7.35 e to the 4 divided by 1200. Actually, no, it can't be 1200 because I now have that 400 kilograms of people up in there, or 300 kilograms of people up in there. So what I'm going to do is make it 300 plus 1200 is 1500. Okay. Everybody follow why I did that? Hopefully y'all hadn't committed too much already. So oddly enough, that, whoa, that's amazing. So this actually gives me 1/2 pi, just the numbers worked out so great. I feel excited to tell you, equals the square root of 49.00 seconds to the -2 power. So I kid you not. So I'm going to take this 7, I'm going to divide it by 2 times 3.14159. That's going to give me 1.114. Actually, that's more than enough sig fig, so I'll just call it 1.11 hertz. So that's the actual frequency. And now if we want to know the period, we just say the period t is 1 over the frequency. So I'm going to raise this number to the -1 power. And that gives me 0.898. And that's just seconds. And that's our period. Any questions on that? Okay, so that's example, I'm going to call this 14.3 because it's essentially the same as 14.3. So I'll just put that there. And we're looking pretty good. So anybody have any questions on that? Does that make sense? Now, it can be a little more abstract than that. So anytime you see something that's oscillating in real time, you can sort of model that with a as the harmonic oscillator. And you can even do so when it doesn't make much sense. Like for instance, your book is getting ready to do an estimate of a spider web. So a spider web doesn't in any real sense seem like a spring, but still, if you see it oscillating, then it's got something that's acting like a spring, because obviously the solution is something that's sinusoidally bouncing up and down. So that's what we're going to do here. This is example 14.4. So what we're going to say is the spider web has negligible mass, say a spider of mass 0.400 grams, has a massless, and again, that just is me telling you, assume it's massless. It's, it's obviously a way smaller mass even than the spider. So it has a massless web and a disturbance causes it to oscillate at 15, let's say at 13 hertz, 13.0 hertz. What I want to do is estimate the spring constant. In other words, we're pretending it like it actually is behaving like a spring. So I want to estimate the spring constant. Actually, I should probably write the word constant if I'm going to do it like that. And B, I want to Shawnee, will you text Austin, let her know I'm in class, baby? Okay, so I also want to figure out what would happen is what would the frequency be if another critter was on the web and had a mass of let's say 0.890. No, I don't want that. I want 0.089. No, I don't want that either. I want 0. Yeah, I do that. That'll be fine. Okay. So let's do our solution. So again, we're just going to go on the assumption that this is behaving like a harmonic oscillator. And with that being the case, we've got omega is equal to the square root of k over m, but that's also equal to 2 pi f. So we can say that square root of k over m is equal to 2 pi f. We can square both sides. We get k over m is equal to 4 pi squared f squared. So we can finally say that k is going to be equal to 4 times pi squared times f squared times m. So we say 4 times pi squared times 13.0 hertz squared times 0.400 grams. Oops. And I have to convert that to kilograms. So I'll say I'm going to get rid of the grams and just say 0.400 times 10 to the negative third kilograms. Remember, the SI system requires us to use kilograms. So now I'll take 4 times 3.14159 squared times 13 squared times 0.4 e to the negative 3. And that gives me 2.67. And that is in newtons per meter. Does that make sense to everyone how we did that? That's part A. So again, even though it's not necessarily a spring, if you wanted to write out a differential equation and have the differential equation oscillate at 13.0 hertz or have the actual solution of the simple harmonic oscillator vibrate at 13.0 hertz, and this would be the x equals a cosine omega t plus phi. This would be the very omega that you'd have to use. In this case, we're just calculating f, but we can now get omega if we want it. Now for part B, what we're saying is let's regroup and now let's figure out what the frequency will be in this case. So now for part B, I'm going to say 2 pi, oops. So that was part A. For part B, I'm going to say that 2 pi times f is equal to the square root of k over m. And this time I want to actually solve for f. So f is going to be equal to 1 over 2 pi times the square root of 2.67 newtons per meter divided by, now I've got not only the mass of the spider, but I've got the mass of the spider plus the other critter. So it's going to be 0.489 times 10 to the negative third kilograms. So if I take the square root of 2.67 and I divide that by 0.489 e to the negative 3, I get 73.88 And that would be divided by 2 pi. In other words, that's after I took the square roots, what I got 73.88. So I'm going to divide this by 2 times 3.14159, close parentheses, and this gives me 11.8 hertz. So the frequency was 13 hertz, but by adding more weight on it, the frequency went down, and the new frequency is in fact closer to 12. So any questions on that?
I don't have a question on that example, but can you scroll up to the previous slide again? I wanted to see those equations you wrote down, like the
Yes.
derived one.
I boxed them off in the red, and then I underlined them in the blue at the very top.
Okay, awesome. Thank you. I took a screenshot of it, so thank you.
Okay, no problem. All right, so another thing we need to understand is how is this simple harmonic oscillator, how does it relate, for instance, to things like velocity and acceleration? So I'm going to do that now so that we can do other problems. So let's break that off. So we still have the idea of the simple harmonic oscillator, and the simple harmonic oscillator has that x, has that x of t is equal to a cosine omega t plus phi. So that's in the raw state where you haven't applied the initial conditions or anything like that. But what we know is that v of t is dx over dt. So let's go ahead and compute that. I'm going to say v of t, and I have the a that's going to be there, but I'm going to take the derivative of the cosine of this function u, and then of course by the chain rule I've got to take the derivative of that function u with respect to t. The derivative of cosine is negative sine, so I'm going to write sine of u, which is sine of omega t plus phi, and now the derivative of omega t plus phi with respect to t is omega. And I think you see that obviously, just like the motion, which is going to oscillate back and forth between a, negative a, negative a, so on and so forth, this v is going to oscillate back and forth between omega a, negative omega a, omega a, negative omega a. And in fact, that is equal to negative v max times the sine of omega t plus phi, where v max is equal to omega times a. So that's a brand new expression that's kind of helpful. And this is a brand new expression that's kind of helpful. Now we also know that a of t is equal to dv dt. Of course, that's also d2x over dt squared. So we can do that as well. Of course, you can start to see now why it's more convenient to write x double dot and x dot. But anyways, a of t is going to be the derivative of negative omega a sine omega t. So again, we're going to have an omega a out in front. They're constants. Then the derivative of sine is cosine of u. And then the derivative of u is, of course, omega. So I'm going to make that. And then the negative was already there as well. But again, you see this is some number times the cosine omega t plus phi. So evidently the acceleration is going to oscillate back and forth between omega squared over a, negative omega squared over a, omega squared over a, negative omega squared over a. So this is also going to be equal to negative a max cosine omega t plus phi, where a max, you can write it as omega squared a, but it can also be omega v max. Okay, so that's another result that we can make use of, and that will come in handy. So for instance, let's look at another example. Okay, this will be example 14.5. That was a nice little heart attack for me there. I think our dog's just knocked over something. So this is example 14-5 roughly. A large motor in a factory causes the floor to vibrate. Okay, so a floor vibrates at let's say at 11.0 hertz with an amplitude of about 3.2 millimeters. Now, what I want to know is estimate the maximum acceleration and maximum speed of that part of the floor. So again, this is something that doesn't necessarily look like a mass on a spring, but it's behaving sinusoidally, so let's go for it. So here's our solution. So what we have is F is equal to 11.0 hertz. That means omega, which is 2 pi times F, is going to be 11 times 2 times 3.14159. That gives me 69.1. And I'll carry one extra sig fig, so it's 69.11 radians per second. So what we know is Vmax, which is the second part they're asking for, but we're going to solve for that first, is equal to omega A. And we also have A is 3.2 millimeters. So it looks like this one we're only going to have 2 sig figs, but that's okay. So this is going to be 69.11 radians per second times 3.2 times 10 to the negative 3 meters. And that'll be times 3.2 e to the negative 3. That gives me 0.221 meters per second. So that's a pretty significant speed. 0.221 radians, or excuse me, meters per second. And sorry about that blue decimal place there. So that's one of the parts. Now the other part is A max. So A max, and this is the part that would actually matter, for instance, to an engineer that would walk in the room and want to decide whether there's a problem. This one's going to be omega squared A, but that's also omega times V max, which is the way I usually like to write it. So I'm going to say that 69.11 radians per second times 0.221 meters per second. And that gives me about 15.3. That's one extra sig fig, 15.3 meters per second every second. And that's the actual acceleration. How does that stack up to G? Anyone? You see, it's bigger than G. So imagine this. the floor reaches the bottom. Okay, so the floor is oscillating back and forth like this, right? It reaches the bottom. That's when it's at the amplitude, but in the negative direction. But then it starts to accelerate upward. And just as it reaches the perfectly level spot, that's when the velocity is 0.221 meters per second. Okay, so it's going to come to a stop. The floor or essentially start to slow down when the actual floor and the actual furniture that might be sitting on it is moving at 0.22 meters per second. Now, the only thing that's pulling on the furniture would be gravitational acceleration. That's trying to pull it down at 9.8. And the box is actually going to start decelerating, and it's slowly going to reach a maximum of quite a bit greater than 9.8. So there's a good chance that when it reaches that equilibrium point where the floor is level, the actual furniture on it might get thrown in the air. In other words, it might the ground or the floor might actually slow down at a quicker rate than the chair does or the furniture does. And then what's going to happen is it's going to reach its max height and then start accelerating downward at a rate greater than g. So even if it didn't get launched off before, when the floor starts to fall, the furniture that's sitting on it is only going to be able to fall at 9.8. So the furniture is going to fall down and go boom, boom, boom. So yeah, that would cause some real wear. That would also be what's called a live load. So if you were in engineering, you'd have to go in and say, okay, well, we've got a floor now that's subject to a live load, and I got to make sure that that happens. The best thing would be for me to sure it up enough that it isn't going to oscillate at such a large frequency so that we can get a smaller acceleration less than g. But if we can't do that, the bare minimums, we need to be able to make sure the floor doesn't just bust as a result of that. So now we're going to have to add a live load in addition to the dead load. So when you're doing, engineering and you're speccing floor joists, for instance, there's usually an amount that the code requires you to allow for a dead load, or you just calculate. I always calculated mine, so I never really knew what the dead load that most places recommend. I think it's on the order of 10 or 15 pounds per square foot, something like that. I'd normally calculate it sort of conservatively. And then that's just basically the weight of the floor, the weight of the joist, the weight of the plywood, the weight of the nails, the weight of the carpet, or if you're thinking about tile, you even might have to account for the weight of the tile. That's all dead load stuff. And then code requires you, like in a bedroom, to allow for 30 pounds per square feet in a bedroom. So you're literally going to imagine, in addition to that, you've got a live load of 30 pounds per square feet everywhere. And now, in addition to that, we also got to add basically 15.3 meters per second times whatever live load you could have on that. That could be a problem, or whatever dead load you could have on that. So anyways, that would ultimately do it. And you have to, in terms of engineering, just in case you're wondering, there's three things you got to test when you're designing, for instance, a floor for floor joists, whether you're going to use 2x8s, 2x10s, 2x12s, or some kind of engineered pieces of lumber. Basically, you check it in shear. Shear almost never fails, but it does when you have point loads. That's a good time for shear to fail. Then you've got a failure in bending that you got to check for. So that's where you're using your moment diagrams that you might have learned about in statics. You're going to use your moment diagrams. You're going to find where and what the maximum bending moment is. And then you're, of course, going to use the cross-sectional area of various lumber to figure out what best member to use, whether it be a 2x8, 2x10, 2x12, double 2x10s, double 2x12s, all that kind of stuff. And then lastly, you've got to allow for deflection, which you guys probably haven't learned about. That's in strength of materials. That's actually a third order differential equation that you got to solve for that. When you get that, you actually get the bending moment for a certain load distribution. And most code says something along the lines of the maximum deflection is L over 120 or L over 240, something like that. So for instance, if it's L over 240, what that means is if you had a 10-foot span then it would have to deflect no more than half an inch over that 10-foot span. So, you know, you can imagine a 10-foot span would be 120 inches. So you're allowed to go up to L over 240. So that's only a half inch. And in fact, it's almost always that deflection is the most important criteria. If you keep the deflection down, you're probably going to keep the bending moment down, but it's not always. So you got to check all three of those, including the shear. And like I said, the shear almost never causes it. Any questions on that? All right, so that's just some stuff that I used to do. We've already handled something like example 14.6, where one of the key things you got to be able to do is if someone tells you that something is oscillating sinusoidally and they give you the actual function like x equals 0.30 meters times cosine 8.0 t times radians, then that means that's the equivalent of x equals a cosine omega t plus phi. So the thing being multiplied by t is omega. So you can tell in that expression that omega must be 8.0, and you can tell that a must be 0.3 meters, and so on and so forth. So that's something you got to be able to do. You'll see that when you start taking practice tests for the final exam. And I still haven't decided, but we're probably not going to have another test for just chapters 11 and 14, or even 11, 14, and 15. So I'm probably just going to make a final exam with that. I don't know. I might make at least a practice test for that and not necessarily do a test. But anyways, that's something you got to be able to do. In this case, we are going to talk about a cone of a loudspeaker. So let's imagine a speaker. So this will be example 14-7. So the cone of a speaker vibrates at 262 hertz, which your book is kind enough to tell you is middle C, and with an amplitude of, let's say, 1.04 times 10 to the negative fourth meters. That's the amplitude. At t equals 0, x is equal to the amplitude. So that's some initial conditions. Now, A, we want to know what describes the motion. And then for part B, we want to know what are V of t and and A of t. And then finally, let's say C, what is x of t equals 0.00100 seconds. Okay. So it's oscillating. That tells us we can go ahead and write out what is its x of t. So for part A, I'm going to say x of t is equal to, now they did tell us the initial condition is that at t equals 0, x is equal to a. So I'm going to put the a right here, and I'm going to say the function is cosine omega t plus phi, like that. Now, what I have to do is I have to calculate omega, and omega is equal to 2 pi times the frequency, and the frequency is 262. So I'll say 2 times 3.14159 times 262. That gives me 1,646 radians per second. Of course, that's using one extra sig fig. So I should really call that 1.65 times 10 to the 3. And that works as fine as well. Now, like I said, they said x of 0 is equal to a. So I'm going to say a is equal to a cosine omega times 0 plus phi, which means 1 is equal to cosine of phi. And that means phi could equal 0, or it could equal 2 pi, or it could equal negative 2 pi, ... all sorts of stuff like that. So we've got that. Now, what we also want to do is go ahead and write what we know. I'm going to assume, because they gave us no other information about the velocity, I'm going to go ahead and assume that phi equals 0 is sufficient. So I'll say x of t is equal to 1.04 times 10 to the negative 4th meters times cosine 1.65 times 10 to the 3rd radians per second times t, like that. And that's going to be the actual answer to part A. Now for part B, they want to know V of t. So V of t is equal to negative 1.65 times 10 to the 3rd radians per second times 1.04 times 10 to the negative 4th meters times the sine of 1.65 times 10 to the 3rd radians per second times t, like that. So I can finally say that V of t is equal to negative 1.646. I'm using my extra sig fig, e to the 3 times 1.04 e to the negative 4, and that gives me 0.171, and one extra sig fig will be 2, and that's meters per second with one extra sig fig times the sine of 1.646 radians, or actually, I'm going to take away that decimal and just say 646 radians per second times t, and that will be our velocity as a function of time. Okay. And now I'll go back to part C, or actually, no, it's still part A. We have to know the acceleration as a function of time. The acceleration as a function of time is still going to have the negative, but now I take this 0.1712 and multiply that by omega, which is times 1646. And that gives me 281.8. Carrying one extra sig fig. That's meters per second every second times cosine of 1646 radians per second times t. So the thing you got to do when you're doing this is you either got to take the time to convert whatever your argument inside of cosine is, you got to convert that to degrees, or you got to put your calculator in radian mode to actually compute this stuff. So just keep that in mind. That's a very common mistake, and it's one that your test banks are normally kind enough to include as one of the multiple choice answers. Anybody have any questions on that part? All right, so part C, they wanted to know what is x of t at 0.001 seconds or at 1 millisecond. So we're going to do that. We're going to say x of 0.00100 seconds. Now, what this is again, a chance for you to double check to make sure you really know how to do this. I'm going to write 1.04 times 10 to the negative fourth meters times cosine. Again, I'm going to use the extra sig fig 1646 radians per second, like that. And then I'm multiplying that by 0.00100 seconds. So I'm going to take that 1646 1646 times 0.001, and that gives me 1.646. And now I'm going to convert that to degrees, and I'm going to do that by dividing by pi and then multiplying by 180. And that gives me 94.31 degrees. So now I'm going to take the cosine of that, and that gives me a negative 0.075. One three. That's the cosine, and I'm going to multiply that by 1.04 e to the negative fourth. This gives me negative 7.814 times 10 to the negative 6 meters. So x of 0.00100 seconds is actually equal to negative 7.814 times 10 to the negative 6 meters. Anybody have any questions on that? All right. So that's a typical sort of problem you have to be able to do with this. What I'll tell you is next we're going to examine basically the damped harmonic oscillator. You can see some other examples up here and how to calculate them. They're not too difficult, I don't think. You'll notice, for instance, example 14.9. So I'm going to say, watch out. And I'm going to say, use my general solutions. Remember that what I did at the beginning of class, I derived formulas for phi and a. Use that, and then also, of course, make sense of the fact that in this particular angle, in this particular problem in 14.9, they're saying that you stretch or actually compress the spring to negative 0.100 meters. So that's in the negative direction. And then you give it a velocity in the positive direction. So when you're trying to map a function like x of t equals a cosine omega t plus phi onto that, then what it's picturing is that the initial x0 is not the negative 0.100. It's some distance back further than that, where it would have been zero velocity at that particular spot, and such that once it got to negative 0.100 meters, it would then finally reach the speed that it's telling you, which is 0.400 meters per second. So you got to watch out. That x0 is not the x0 that we solved for. That's just the x at t equals 0. So you can still plug it in, but what you got to realize is when V of t, where t is just slightly bigger than 0, that's got to be in the positive direction. And that starts off, V of t is negative omega a sine. And the only way you can make that a positive velocity is if the sign is negative, and the sign's not negative, S-I-N-E, the word sign, that is not negative until you get past pi. So you've got to actually be in the third quadrant for that. That's going to help you adjust the angle for phi. In other words, you're going to get a phi that's in the first quadrant. And in order for you to get it to the third quadrant, you add 180 to it, and that'll help you. So anyways, I want you to do that. Add 180 degrees to go from Q1 to Q3, quadrant 3. Okay. So hopefully that'll help you. Now, the next part we're talking about is a little more advanced, and we're going to actually, let me go ahead and do the energy part first. So first off, I'm going to tell you the energy part. So we have X is equal to A cosine omega t plus phi, something like that. And that's all well and good. You also have V is equal to negative omega A sine omega t plus phi. Okay. So if you talk about energy, you're going to have 1/2 k x squared plus 1/2 m v squared. That's going to be 1/2 k times a squared cosine squared omega t plus phi plus 1/2 m times omega squared a squared sine squared omega t plus phi, like that. And with that, you can see that you have a 1/2 k a squared. And you would really like to have some way of relating that 1/2 m omega squared a squared to k a squared. So what you can do is you say E is also equal to 1/2 k a squared, but it's also equal to 1/2 m v max squared. Well, v max is omega times a, so I'll square that, and I get 1/2 m omega squared a squared. So we see that 1/2 k a squared is equal to 1/2 m omega squared a squared. Or you could just realize that from k equals the square root, or excuse me, from omega equals the square root of k over m. That's another way you can do it. But the main thing is you now see that I can replace all this with 1/2 k a squared, just like that is. So now what I'm going to do is say this is cosine squared omega t plus phi plus sine squared omega t plus phi, like that. And of course, cosine squared plus sine squared is just 1. So you clearly see that the energy is 1/2 k a squared. Of course, you could also do it the other way by getting rid of the 1/2 k a squared, and you'd also come up with the same result. In this case, you'd have 1/2 m omega squared a squared. So that's really what these energies are. That allows you a whole different way of looking at things. You can say 1/2 k a squared is equal to 1/2 k times a squared cosine squared omega t plus phi plus 1/2 m omega squared a squared sine squared omega t plus phi, something like that. And if you wanted to take that further, you can actually figure out what V would be. So you could just call this right here, instead of calling it omega A times sine omega t, you could just call that V squared. So then you'd have 1/2 K A squared times 1 minus, in this case, we'd say, pulling the other part to the other side, we're going to have 1/2 K. In this case, I'm just going to call that X. So it would be minus X squared. No, I don't want the KA squared. Sorry about that. Let me start over. So we have 1/2 KA squared is equal to 1/2 K X squared plus 1/2 M V squared. So we can actually solve for that by saying 1/2 K times A squared minus X squared is equal to 1/2 M times V squared. So the 1/2s clearly cancel out. And ultimately what we get is V is equal to the square root. Now get this, you're going to divide by M, so you end up getting K over M, which is just omega, times A squared minus X squared. Okay, now that one's bad. And that's plus or minus on that, which you might also notice you can factor out an omega times A in there, and you'd say V is equal to, oops, let's go ahead and write it in blue still. So I can say V is equal to plus or minus. So K over M is omega, and A, or excuse me, is omega squared, and A squared. That gives me omega A, and then all I have to do is say 1 minus X over A quantity squared, like that. So that actually gives me an expression for the velocity at any point X. In other words, I now have a velocity as a function of X as opposed to a function of time. And you can do the same thing, for instance, with the X. You could get it as a function of velocity if you really wanted to. So that's kind of neat. That's kind of helpful. And that's how the energy calculations basically go. You can see how that works out. The next thing I wanted to go ahead and do, we'll do some more examples with this next meeting, which would be Monday after the break. But I'm going to move on to show you that this actually is handled by some other stuff as well. So for instance, one thing, your book takes the time and shows you that simple harmonic motion is exemplified by rotational motion. So if you actually go in a circle at a constant speed, you can imagine that at least the X component of it is moving back and forth with that exact same shape. So when you say X equals A cosine omega t plus phi, that does describe something that's oscillating back and forth in time, but it also specifies, let's say, the shadow. If the sun is directly overhead, it would basically specify the position of a shadow of an object that's going in a circle like this at a constant velocity v, or constant speed v, and the shadow of it would just be that X, and it's still the X equals A cosine omega t. And that's basically what they're showing in section 14.4. So it's kind of neat, and it's exactly right. So X equals A cosine omega t plus phi is exactly the right expression for relating it to a circle. You just have to realize that the angle that the thing makes, so if you drew a line from the center of the circle to the object that's going around the circle, that length of that line, of course, would be the radius of the circle, but the X component of that sort of vector from the center to the position, that X component is given by A cosine omega t plus phi, but omega t is just the angle theta that it's moved counterclockwise from the positive x-axis. So that's a kind of neat scenario. Your book takes the time to do that, but your book also takes the time to show that for a pendulum, for instance, let's do this. So for a pendulum, it turns out that you have a mass hanging from a ceiling, say, and that mass has been pulled out an angle theta, and it has a mass m. What we know is that there is a tension force T that goes that way, and then there's a force mg that goes this way, and that could be broken into, because this also is, or actually, excuse me, this also is theta. So, dang it. So this one would be mg sine theta, and this part would be mg cosine theta. But the main part that we see is that the f in the theta direction really is f is equal to negative mg sine theta. And if you assume theta is small, then sine theta is approximately equal to tangent theta is approximately equal to theta, and we'd say f is equal to negative mg theta. And then we could also use, realizing that this is L, for instance, is the length of that, we could see that theta, which is supposed to be also tangent theta, which is also supposed to be sine theta, is mg, it'd be s over L. So s over L, meaning s the arc length, and then L would be the length of the pendulum. When you get that, then you get basically m d2, actually, excuse me, m d2x over dt squared, or actually in this case we're going to say d2 theta over dt squared is negative mg theta, something like that. And you could even say it's s if you wanted to, and go with that. But the main thing is you can see that that's basically another simple harmonic oscillator. So that works. There's another case you can handle as well, and that is a physical pendulum. And your book talks about that as well, but we're out of time, so I'm going to go ahead and let it go. And you guys are free to go. We'll finish up some more of that later. We'll finish out the damped harmonic oscillator as well as chapter 15 we'll do. Okay. So thanks for coming, everybody. I'll wait for the last person to leave in case anybody has any questions. And you have a good one. Thank you for coming.
So for the Pearson assignments, what
Mhm.
exactly is assigned to us?
What is what to you?
Like what are the rest of the assignments that are assigned to us by the end of
Okay,
the
gotcha.
semester?
So what's going to happen now is we're going to have 14 and 15. Those are the only ones that are left that are required. Everything else is going to be extra credit. So you've
Okay.
got 1 through 10, no, 1 through 11, and then 14 and 15. So 12, 13, and anything after 15, all of that's extra credit you're welcome to do. And I would say it would help you to do them unless you're just, looking them up, in which case it's just getting you free points. But the free points don't help that much unless you've missed some homework. So I would say it's not worth your time unless you really missed a lot of homeworks and you want to bring your grade up that way.
Okay, thank you.
Help.
Have a good night.
Okay. See you, Jacob.
Hey, Professor Younger.
Yes.
So what exactly are the extra credit ones? It's Newton's like special theory of relativity and elementary particles. Is that it?
Yeah, I think that's chapter 43, if I remember correctly. So yeah, those are eligible. Any of them that I have out there that are not 1 through 11 are 14 or 15. All of those are extra credit, even if I didn't put the EC or the word extra credit on it.
Also, would it help to take those in preparation for like a 242?
I would say maybe a little bit with relativity. The chapter, I think it's 36, but not too much beyond that. I would say that chapter 12 is static, so that's sort of like what you do in your
Yeah.
statics class, so that might be interesting. 13 is fluid mechanics. I would say that would be helpful for your future, just in terms of you're ultimately going to have a fluid dynamics course for most engineering's classes, and if you had any experience with it, that would be helpful. So I would say probably the most important is 13, the second most important is 12, and then 36 is the most important after that.
Oh, I gotcha. Yeah, no, I was just wondering because I wanted to do like double E or like computer engineering. So I really want to focus on like 242. So I was just wondering if anything would like carry over to that.
Yeah, the
Because it's
relativity is
particles.
pretty helpful on that, just because
Yeah.
it's neat. But when Maxwell made up Maxwell's equations,
Mhm.
which basically he just copied Faraday's notes and then found
Oh.
one problem and fixed that. But all of those equations came out relativistically correct. So a lot of times, any electricity and magnetism course will include a relativity section. So yeah, I'd say the relativity might be helpful on that, but that's about it.
Okay, yeah, that's cool. All right, thanks, man.
You're welcome.
Yeah, I'll see you next week.
All right, see you. Thanks for coming. Looks like that's it.